and let me try recording here also as a backup. Okay, so yeah, good morning everyone. Sorry for the my mic problem. But hopefully now everything should be working. Everyone can hear me now. So if for some reason my mic stopped working again, just let me know. And hopefully it's fine now. So let's yeah, any other issue? Let's check. Okay, good morning everyone. Yeah, so I don't know how to read Chinese, so I don't know what were you saying. Okay, so let's start with the lecture. We are continuing on chapter 2, which we were talking about. What we were talking about is the Newton's law, right? So let me open the lecture notes again. We are talking about Newton's law, and in the previous week we were discussing the first law, systems in equilibrium. So now we will continue on the second law and the third law, which is second law is the one that everyone is probably something that everyone who has learned physics in high school have been familiar with at some point, right? F equals to ma. So it is basically how to calculate the acceleration of an object once we know the net force. So the second law, as we can see, right, full screen, as we can see, the second law is essentially the generalization of the first law. So for the case of zero acceleration, then we just have zero net force, and we come back to the equilibrium, which is the case that was covered in the first law. So actually the first law is just a special case of the second law, if you think about it in that way. So the second law by itself, right, as we write it here, yeah, let me start by writing this down. Okay, so the second law looks very simple, but as most students will experience, right, although it looks very simple, but sometimes the situation they encounter will become more and more complicated. So we need to really understand how the second law works. Okay, so let us define. We let F be the net force acting on an object. Okay, so we have a net force acting on an object of mass m. Okay, so m is given in kg usually, or grams, depending on the situation. Then the acceleration of the object obeys the equation, or satisfies the equation F equals to ma. Okay, so this is force, and then mass times acceleration. So now, as long as this term is no longer zero, this is the general case that should allow us to study the behavior or the mechanical motion of all the situations that we will encounter in most of everyday life, right? So we are talking about Newtonian mechanics, which where the forces and the accelerations are in the order of what we see in everyday life, like a car, right? And the forces are like objects hitting, collisions, and things like that. So this law will no longer be valid if you are moving very close to the speed of light. We will learn more about that in chapter 10. So for now, we learn about more of the everyday scale of the object, and we use this equation to calculate. Okay, so the main challenge or the main difficulty is how to determine F. Once you determine F, we can get A already. Usually A is very simple, or just getting A is either given you calculate F, or you given F calculate A. Most of the time, the biggest challenge is to how to calculate F, and the key point is you need to be able to draw the free body diagram to get the forces correctly. Okay, yeah, just checking if there's any question. So yeah, so how do we well, before we continue, right, now that we have the equation and now the right hand side is no longer zero, we can now determine the SI unit of force. Okay, so we can now fix the SI unit for force. We have been calling this Newton, but we can express Newtons as a combination of SI units. So we can now fix the SI unit of force. Because the right hand side is these two things, we know the SI unit, so we just combine them, we can calculate the SI unit for force. Okay, so in other words, the dimensions of force is equal to the dimension of the right hand side, which is dimension of mass times the dimension of acceleration. So the dimension of mass is just mass, right, kg, and then acceleration is lt minus 2, okay, meters per second squared. So in other words, we can insert the units here. The SI unit for mass is kg, remember, SI unit for length is meter, and SI unit for seconds for time is seconds. So therefore, in terms of SI units, 1 Newton is equivalent to saying 1 kg meter second minus 2. Okay, yeah, so so this is the dimensional analysis part, and from the tutorial that we did last week, right, the lesson that we learned here is, I think a lot of students, they take dimensional analysis for granted these days. They think it's the easy part, so no need to pay too much attention about it, but sometimes you get questions like in last week's tutorial. Okay, so dimensional analysis is quite important, and I was also mentioning last time that dimensional analysis, lacking any further information, sometimes dimensional analysis is the only way we can make progress in a theory. So that's how people in quantum field theory, how they do, right? So they take care of the dimensions, and then just by noticing the dimension, they can find new discoveries. So it's quite important. Okay, so with that, let us look at an example. Okay, so everything looks like it's running. I'm still recording. Okay, so let's look at an example over here. Yeah, so simple example, right? This one everyone knows how to do, but let me just go through them as a reminder or just as a warm-up. We have a mass, 5 kg, okay, sits on a frictional slope with some incline, and then using this, what is the acceleration of the mass? So this should be very simple. As a warm-up and to establish notation, let me show you how I normally solve this problem. So we have, this is example 2.1.6, okay. What I have here is a slope. So I have a slope at an angle, incline, we call this incline alpha, and then I have a box sitting on top of it. So this is smooth. We have not talked about friction yet, we will very soon. But firstly, we want to calculate the acceleration along the plane. Okay, so we know that you definitely accelerate along the plane because you can't pass through this thing, right? And it definitely won't fly off the ground. There's no other external force. So to do this, we will draw the free body diagram. So this object is having mass m. As always, there's a weight mg coming down, and it is touching a surface. So when it touches a surface, we got a normal force, and once we got a normal force, we can get the direction to be perpendicular to the surface. So this is my normal force. The magnitude, don't know yet, so leave it as unknown. We will calculate this later. Okay, so right now we have forces in different directions. So what we can do is we can choose a coordinate system, right? So I'm going to choose the coordinate system where my x is parallel to the plane and my y is perpendicular to the plane. So then I can resolve my forces according to these two components. So I'm going to resolve my normal force over here, my weight over here. So I got mg cos alpha, and then resolve my mg on this direction, mg sine alpha. The n is already in the y direction, so no need to do anything. Therefore, in the direction that is perpendicular to surface, right, all the forces in the y direction is this one and this one. Okay, so my net force in the y direction is this force minus this force, so I got n minus mg cos alpha. I'm writing some extra steps here because everybody knows already, right? There should be no net force along this direction then I got n minus mg cos alpha. So therefore my n is equals to mg cos alpha, right? So see, this time the normal force is not equals to mg. There's an extra thing at the back here. So this is the expression for the normal force. But I'm just showing you how to solve, right? This example is asking you to calculate the acceleration along the plane. So this one is doesn't give you the information. The one that gives you the answer is parallel to surface. Okay, so parallel to surface is my net force along the x direction. There's only one force in the x direction. Okay, so it's this one over here. So it's just mg sine alpha, right? And then by Newton's second law, my net force is equals to mass times acceleration. So I got mg sine alpha. Okay, so cancelling this, then from here I got my acceleration. So g sine alpha. Now, apparently based on our calculation, right, our acceleration is independent of the mass. So no matter what the mass is, the acceleration is always g sine alpha. And we can calculate the number now. So 9.80 times sine of 30 degrees. So if you get everything, you get 4.90 meters per second squared. Okay, so this is the acceleration of the block in the parallel to the plane. Okay, and as we can see, right, the acceleration is given by this formula, so it depends on the alpha. So if alpha is 0, there is no acceleration horizontally, which makes sense, right? On a flat plane, you put something on a flat plane, it's not going to move, right? But if you increase alpha a bit, it will start to accelerate. And if you raise this higher and higher, it will accelerate faster and faster. Okay, until, in fact, you can even calculate until it's go to 90 degrees. So 90 degrees, sine 90 is 1. So at 90 degrees, the acceleration is just the same as free fall acceleration, right? Because if it's vertical, then it's the same as just falling straight down. So we got all the case that we can interpret from this equation here. Okay, so every time we solve a problem, right, we got an equation. Usually in physics, it helps to check against the situation, right? So whether it makes sense or not, right? That is what we mean by interpreting a formula, right? Giving a physical interpretation to a mathematical equation that you derive. Okay, so yeah, so this is a pretty straightforward example, right? I don't think anyone has question. Everyone should be following. Okay, so yep, looks good. Continue. Still recording, and go to the next example. So this is page 1. This is page 2. Okay, so we have the next example. So let's go to the next example. Which is this one over here. Okay, so in this figure, I have a pulley and two masses, and then this is a frictionless pulley attached with a rope. So assume the rope is negligible mass. Given the two masses, what are the accelerations of each mass? So let's try to do this. Okay, yeah, so example 2.1.7. So what we have here is I have a pulley, right, and I have one mass over here, M1, and then I have another mass, there is M2 over here. Okay, so this is a rope, right? It is one single rope attached all the way, so it should have one tension everywhere. And notice that I do not, okay, since this is a picture with multiple objects, right, usually I do not advise drawing arrows here, because you might confuse yourself, or at least I will confuse myself, so I don't want to do that here. I want to draw the free body diagram, because remember, free body diagram is for individual object. So one object have their own free body diagram, and we do not mix up their vectors and arrows. That is where we make mistakes. So what I mean is, we draw the free body diagram for M1. Okay, so for M1, and let's look at what are the forces acting on M1. So M1 is I draw it separately here. M1, as always, it is hanging in earth, so there's a weight mg, m1g, and it is attached to a rope. So attached to a rope, there is a rope of some tension T. Okay, and I'm going to take as upwards as positive. Okay, so if I take upwards as positive, that means I take T minus m1g is equals to m1a. Okay, so that means if I define upward as positive, right, I can calculate a towards the end. So if a is a positive number, that means it will accelerate up. If I somehow calculate a to be a negative number, that means it's coming down. Okay, so that is our situation over here. So this is my first free body diagram, and then secondly, free body diagram for M2. Okay, so M2, since I want to take this as a consistent picture, right, I want to take down as positive for this picture. Okay, so I'll take downwards as positive. You can also take up as positive as long as you follow everything correctly, right? But now let's draw the forces M2. Okay, so if I M2, right, the M2 has a weight and it is attached to the string. Okay, and the direction is always away from the object as long as it is a cable. Remember, most common mistake students do is like they start with the first free body diagram and then they draw the arrow here and then they follow and then they draw the wrong direction. I told you before this right, but I repeat again because every time sure someone will make this mistake, so that's why we do not do it here. Okay, so we only do it here, then everything is correct. We do it here, and then always remember, tension always pull. You cannot use a string to push anything. Okay, so that's why we got this picture. And if I take down as positive, so this thing is positive term and this thing is negative term, and then it will give you M2a. So if I get a to be accelerating positive, that means it's going down. Okay, so the magnitude of these two a's are the same because this is a unstretchable string, so the two will go at the same speed and also same acceleration. Okay, so I got these two equations now. Then normally when you see things, right, if I have two equations, usually it's because I have two unknowns, right? Because I don't know what is t and I don't know what is a, and what we are looking for is the acceleration. So let's try to calculate this. Because I have t is unknown, so I can cancel the t away if I take equation 1 plus 2. So if I take 1 plus 2, I cancel this away, so I got m2g plus m1g. So I got m2g minus m1g, and then on the right hand side is m1 plus m2 a. Okay, then I got the simple relation now, so it's basically m2 minus m1 g is equals to m1 plus m2 a, so I can calculate the acceleration, which is m2 minus m1 m1 plus m2 and then g. Okay, so we plug in the figures given, and is it given? Yeah, so m1 is 2 kg and m2 is 5. So what we have here is m1 is 2, right? So we got 5 minus 2 and 5 plus 2 g. So essentially we got 3 12 over 12 g. Okay, and then you can plug in the number to get the answer. Okay, but let's say, okay, so this is for a given mass, right? But we can again I can show you how is our physical interpretation for this kind of case. So we observe that this is a m2 minus m1. So if m2 is greater than this mass, then my acceleration is positive, right? So if everything okay? 3 over 7, 3 over 2. What do you mean? 3 over 7? Oh, sorry. Yeah, I'm wrong. Or is 2 plus 5, right? 2 plus 5. Correct. Why I put this? So it's correct. Yeah, you're right. Thanks. So the answer is 3 over 7. Yeah, I went too fast. Yeah, thanks, Jia Chen. So this is wrong. Yeah, so it's 3 over 7 g. So what I was saying, yeah, m2 is, if m2 is greater than m1, then acceleration is a positive number. So m1 will go up, m2 will come down. So it will be coming this way. That is correct. So if m2 is heavier, it will pull it down. But if m2 is smaller than m1, okay, so if m2 is lighter than m1, then my acceleration is negative. So if I call this upwards positive, then I get a. That means my m1 is coming down. So it's again, the physical interpretation should be consistent with our calculation, because the heavier one will pull it down, will pull the system down, and then the lighter one gets pulled up because of the pulley. Okay. What is the direction of A? So yeah, so as I was saying lah, right? If let's stick with m1. So for the direction, I call up as positive. If I call up as positive, then my final answer, right, I have positive 3/7g. So that means I have positive, and upwards is positive, so it's going up for m1. Make sense? Okay. Yeah. Okay. Yeah. So there's actually many ways. You can define your coordinate system. You can some in your past you have learned it in a different way, but as long as you follow the method consistently, is at the end of the day it will make sense, right? Yeah. So should I write this out? Okay, so let me write this out. Okay, so for a general case, so for a general case, what I'm just writing out what I just said. What I just said just now, right? If m2 is greater than m1, yeah, just to clarify, also, A is positive. So if A is positive, then what we have here is the m1, then like this, right? So the system is going this way. Okay, so this is m2. But on the other hand, if m2 is lighter than m1, A is negative, so it's going the other direction. So we've got m1, m2, so my system is now going this way. Okay, so these are the two cases. And then if m1 is exactly equal to m2, they're exactly the same weight, so they don't move. Acceleration 0, equilibrium, they balance each other nicely. Okay. Okay, so any questions so far? Okay, hopefully everyone is following. If everyone is okay, we shall continue with the next example. Hang on. No, I think it's third law already. Okay. Yeah, so far, right, the examples that you see here are like it's still pretty simple. It's because right now I'm only sticking to the three basic forces: tension, weight, and normal force. Okay, so those are easy. But after we cover third law, I will introduce to you more forces, and that will be more complicated. But we shouldn't worry yet, I think. Let us learn about third law first. Okay. So Newton's third law. Okay, so this is section 2.1.3. It's basically talking about third law. Okay, so yeah, what's Newton's third law about? I think third law is should be very famous by now. Even people who are not in physics may have heard about the saying, right? For every action, there is an equal and opposite reaction. And if you watch the movie Interstellar, also they use it as a way to escape the black hole. If you remember, there's one scene, right? The rocket ship is falling into the black hole, and then he kind of want to say the third law, but it's more like the conservation of energy, like if you want to go one direction, you need to drop something. I forgot the line already. but if you watch the movie, you probably know what I'm talking about. But anyway, the important thing is we should learn the full expression of the accurate definition, which is over here. The third law, right, is now talking about interaction between different objects. First and second law is about a single object and what are the forces acting on that one object only. Okay, but what if there's multiple objects, two objects? Okay, and then they interact. That means they touch each other, or they have a string or something, right? Normally it's touching. Normally it's about normal force. So if I have multiple objects, object A and object B, and they are touching each other, so what happens? Let's say if object A exerts a force on object B, then by the third law, B exerts the same force on A. Okay, and then the two forces, right, A on B, B on A, they have the same magnitude but opposite directions. Have the same magnitude but opposite directions. Okay, so is there a chat? Because both masses on the same rope, yes. Acceleration is the same because both masses on the same rope. Yes, yeah, Zhihao was also correct. So yeah, the assumption for the previous example is, right, is attached to the same rope and the length of the rope is fixed. That means the rope is not stretching, right? If the rope is stretching, then they can move separately already, right? But if the rope is like, you can't stretch it, it's a rigid rope. If it's a rigid rope, right, then if I have two masses, they have to move at the same pace. Okay, if I accelerate, they must accelerate together. Okay, so this is the assumption that is usually made. Otherwise it's more complicated to solve the problem. This is a light, in the textbook they call it light, non-stretchable or inextendable rope. Okay, and we have to make this assumption because if the rope can stretch, you cannot really solve this question anymore, right? Why? Because if the rope can stretch, then you need information how much the rope can stretch, right? What is the so is it like a spring? Does it obey Hooke's law, or is there a maximum stretching, right? Sometimes some rope can stretch a bit and then maximum no longer stretch anymore. So there's a lot of factors to take into account which we cannot solve. That's why we assume this. Yes, yeah, another way of saying is the rigid rope. Yeah, okay. Now, about the third law, right? How do we handle the third law? So, so let's here. Usually it's about, as I say, right, two objects. So let me draw a simple situation that is in the lecture notes. The first scenario is that I have a box, okay, and then this is object A. So object A has mass A, and then object B has mass B, okay, and this is one sitting on top of the other, and there's going to be a normal force. So let us do our usual thing. We try to draw the free body diagram. So the free body diagram for object A is like this, right? So object A is MA. Okay, what are the forces acting on MA? Always there's a weight. Okay, and then so it is sitting on the floor, so there should be a normal force from the ground. Let me draw the arrow here, not enough space. Okay, so this is the normal force from the ground. Okay, but that is not what we are focusing on at the moment. There is a object B sitting on top of A. So when there's something on top of A, that means something is pushing down on the ground, right? If you put something on your head, you will feel something on your head because it's the normal force, right? So this is the normal force. We said on A acting coming from B. Okay, so this is the free body diagram of the normal force of B acting on A. Okay, and then we look at the free body diagram for B. So free body diagram for B is over here. This is MB. Okay, and MB is sitting on the other object, which we are not drawing fully because we are not we are only focusing on B. So there's the weight as usual. Okay, and it is sitting on top of some surface, so there's going to be a normal force, and this normal force is coming from A, right? So it's coming from A, so that means this is the normal force on B coming from A. So according to Newton's law, okay, this is the B exerting force on A, this is the force on A exerting force on B. So these are the action and reaction forces. Okay, so these are opposite direction and having the same magnitude because of third law. Okay, so yeah, do you follow so far? I mean, this is probably something that everyone understand already. I'm just saying a lot of extra terminology and definition, but hopefully, yeah. So if anything is not clear, you can ask me. Okay, so so this is the third law, right? So that means, right, according to this situation, if I were to write everything in a mathematically consistent way, we say that by Newton's third law. Okay, so these are vectors. Okay, so if I say that this is a vector of B acting on A, okay, then this is by Newton's third law is exactly the negative of the other one on this. Okay, and then if I say the magnitude, they are the same. Obviously, right, from this equation you can already say. Okay, now let's look at another simple situation. Let's say this is in equilibrium. Just now it's in equilibrium, but what if we are talking about a moving system? It still can be solved in the same way. So let's say I have M1 here, and then I have a M2 here, and then I have an external force acting on this object. Okay, and let's assume this is a smooth floor because we haven't talked about friction yet. That will be coming soon. So this is the external force acting on this. Okay, so how do we solve this problem? Sometimes the question may give you this picture, ask you to find the acceleration. It may ask you to find the normal force of 1 acting on 2, 2 acting on 1. It can yeah, so you might be asked to find all kinds of things. So let's try to draw the free body diagram for M1 only. Okay, so let's consider the forces acting on M1. Okay, so M1 is like this. Okay, it is there's M2 over here, but we do not draw it because we're not looking at forces on M2 yet. So what are the forces acting on M1? Okay, so this is the external force that is exerting on M1. So I have one force here. M1 has a weight, and there's a normal force coming from the ground, but we do not care about the vertical force at the moment. And then M1 is touching M2. So when you're touching something, usually there is a normal force. So there's a normal force that is I'll just call this N, right? This one is the normal force with the ground. I don't care, right? Normal N ground 1. Okay, so there's a normal force over here. So if I just look at the horizontal forces, if I take right as positive, then F1 minus N is by Newton's third law is the net force. So the net force, it will give you the mass times the acceleration. So this is equation 1, right? Then you look at the free body diagram for M2. So M2 is this thing here on the smooth ground. Okay, M2, and then it is touching M1. So if it's touching M1, what are the forces acting on M2? So M2 is, yes, there is the vertical force, but I don't care the vertical force at the moment. It is touching M1, right? So it's touching M1. So it's touching M1. So there is a normal force. The normal force is usually what I call a touching force, and it is the same N by Newton's third law. So these two are the same. Okay, so these two are the same magnitude, just that they have opposite direction. Okay. Now let me ask you this question. F0. So can I put F0 as my external force acting on M2? Yes or no? I'm sure some of you might say no, right? So yeah, correct. No, that's right. Although I think some will make a mistake and forget they'll put F0, right? So this is the thing about the free body diagram. It's always acting per object. So M2, we only look at forces acting on M2. This one is very far away. So very far away, it's not acting on M2, right? It's only acting on M1 directly. Okay? So, but the picture should still be consistent. If the external force is not acting on M2, right, then how can it accelerate? Well, there's still the horizontal force here. So by Newton's second law, the only horizontal force acting on M2 is this N, and then I got M2A. Okay, and we can see by solving this equation, it's consistent. The whole system will still accelerate. So let's try and solve this. What is the we can, let's say I know, let's say this is given to be, I don't know, something 10 Newton, right? So this is maybe 1 kg, this is 2 kg. What is the acceleration? I can solve this. So I can take equation 1 plus 2. Okay, so 1 plus 2. This plus this, so if I take 1 plus 2, right, the n cancel each other. So F2, and then this plus this is just M1 plus M2 times A. Okay, so the acceleration is something that we can calculate it. Okay. So so we can still calculate the acceleration. Notice that this equation, right, this is the same equation you got if I consider M1 and M2 as a single object. Okay, so in other words, we get the same answer if we treat M1 and M2 as a single combined object, okay, of mass M1 plus M2. So that means instead of looking at them separately, right, the picture I'm going to draw is just a single combined object. So it's just one big piece. The total mass of this whole thing is M2, and I'm just exerting a force F0, and then based on Newton's law, the net force acting on this is F0, so M1 plus F2, it will give you the acceleration. Okay, so that means you can still get the correct answer anyway. That's why it's the consistent picture. And the reason why this is consistent is because these two n must be the same magnitude. So if it's the same magnitude, this operation can cancel it out, and I will get this consistent picture. So Newton's third law is necessary to get a consistent picture over here, right? Otherwise, if third law is not true, you get a weird situation. If you push something, right, then these two n are not the same. If these two n are not the same, then you might get different acceleration and different forces acting on it, and then it will deform the situation in that does not happen in nature. Okay, so another way of saying is that so here is the n between A and B cancel out. Okay, so the reason they cancel out is because this, another way to say, these are internal forces. Okay, so they will cancel out when we look at the system as a whole, right? So if you look at the system as a whole, the normal force, they cancel out. That means they do not appear anywhere in the equation, right? So let me try to explain one more time. If the Newton's third law is not true, if we don't have Newton's third law, then these two, let's say they have different magnitude. If they have different magnitude, you take equation 1 plus 2. If the n do not cancel out, then you get some extra thing over here, okay, which is nonsense, right? So how come if I put a force, then I get some extra force out of nowhere? So that's why this do not happen, and this do not happen because of third law. So that's why third law is important to make sure everything in nature, if you push something, everything works consistently. Okay, let's check. Yeah, so everything should be okay. Any questions so far? Okay, so if not, right, so that is essentially, I have covered all the Newton's law already, right? So I have taught you Newton's first, second, and third law already. So actually, right, that's all we need. Everything about mechanics is about Newton's third law, and since I told you third law, everything should be finished, because everything that we will learn after this is just following from the third law. Okay, so is something happening? No? Okay, so essentially we have covered everything that is the fundamental of mechanics already, and from now on, everything that follows after that is just a consequence of the three laws that we have learned. So that is kind of like why Newton is famous, or why the three laws is very powerful, which is to say everything is all compact into these three statements, right? But even though there's three very, very simple statements, there's still a lot of things, a lot of consequences that follow from them, and this is one of the main objectives of theoretical physics, right? We want to describe nature. We want to describe everything that happens, the laws of nature in the universe, on Earth, everywhere, right? So a lot of complicated things happen. This world is a complicated place, but every time we study a certain system, we always find that all these complicated situations always follow from some simple laws. So that is what most of the time, that is what we want to do in physics, right? So we want to derive everything based on simple laws. So but for now, let us continue studying the consequences of these three laws. But it's not really finished yet. So at this stage, right, I am only teaching you the third law using three basic kinds of forces, okay, the normal force, weight, and tension. So in order to get the more complicated situations, we need to look at more new types of forces. So that is what I will do. Newton's laws. This is part 2. Okay, so part 2 is where things get more interesting or more complicated. Okay, so now we have learned Newton's law already. Now we look at more complicated forces. So we are introducing more forces, okay, besides just the standard 3, because standard 3, all the examples that we've been solving is very simple. Okay, what time is it now? Okay, so let me talk a little bit, and then we can rest for a bit. Firstly, let me introduce to you Hooke's law. Okay, now Hooke's law has a very interesting history also. Hooke's law is named after Robert Hooke. He lived in England around the same time as Isaac Newton, and Robert Hooke is the enemy of Newton. Like they don't get along, they don't like each other, and they always argue against each other and things like that. And right now, Hooke is the only place we hear his name, but that shouldn't be so, because Robert Hooke himself is a very talented scientist. The reason why we seldom hear his name, right, is because of Isaac Newton. Isaac Newton is like very competitive, and once he get the power, he wants to erase Robert Hooke's name from like history and textbooks. He take down Robert Hooke's pictures and everything, and the consequence of history is that people seldom hear about his name. We only hear Isaac Newton's name. So again, like Isaac Newton is not really that kind of person either, right? And with egos and everything. But right now we learn Hooke's law, right? So for Hooke's law, it's talking about a spring. Okay, so I have a spring, and let's consider this sitting on a smooth surface, and I shall put this as my x-axis. Okay, so we are talking about a mass m attached to a spring. And let's say, right, because a spring, right, every spring has a equilibrium point, right? A spring, you can pull it. If you pull it, it will try to come back. If you squeeze it, it will try to push out again. Okay, that means a spring always wants to remain at its specific length, which we call the equilibrium point. So equilibrium point, or if this is the equilibrium point, this is the natural length. Okay, so natural length. Okay, so so we say that x is equal to 0 is the equilibrium point. Because when my object is at equilibrium point, the net force on the object is going to be 0. Okay, but if I pull this thing out, okay, beyond its equilibrium point, so if this object is here but it's attached to a spring over here, okay, so the distance is some value of x, and over here x is a positive number. Okay, then in this case the force will try to push it back. So that means it will experience, the spring will try to pull this mass back, and according to Hooke's law, the equation that is pulling is minus kx. Okay, because it's in the negative x direction. Okay, but on the other hand, if I squeeze the spring in the other direction, okay, my equilibrium point is here, so this location is a negative x, this is the origin of x, right? Then it will experience a force that is pushing it in the positive direction, and in this case the force acting on the spring is a positive number, so is I should say that k is still kx, but in this case, right, x is negative, so this is negative times k, and then I have a negative position. So negative times negative is I have a positive force, that's why the force is coming in this direction. So the absolute value of the force is just kx, like this, and the absolute value of this force is kx, like this. Okay, so what time is it now? So that means, right, this is the general expression for the force acting on the spring. So let me write this more clearly, what I just said. What we learn, or what we realize from the spring, is that a spring always push or pull the mass, right? It doesn't, either it's pushing or pulling, is whatever it's doing is want to push it towards the equilibrium point. Okay, so that is the picture I put it here. So if I pull it here, if I put my object here, the spring will try to push it back. If I put my object here, the spring will try to push it back in this way. So we can say that so I can write the Hooke's law in vector form, right? So this is, everything is in a horizontal direction. Then the force acting on the spring, the force due to the spring is negative k, and then x unit vector I. So if x is on the left, of my origin, that means it's a negative number, I get a positive force. If x is on this side, x is positive, then I get a negative force, try to pull it back. It's always negative of whatever this value is, okay? And then this thing here is a constant. So this k is a constant that depends on the spring. So if k is a high number, it is a very powerful spring. If k is a low number, it's a soft spring. The force is very small. So this k is what we call the spring constant, or to use Hooke's name, we call it the Hooke's constant, or sometimes we call it the elastic constant. Even though I draw a picture of a spring, this Hooke's law, it still works for elastic string, like a rubber band, right? So that is a stretchable string, not a rigid rope, right? So that is the how to say, yeah, elastic string. So we call this the elastic constant. Okay, so this is a physical quantity, and actually we can determine the dimensions of this. So let's look at the dimension of Hooke's constant. So dimension of Hooke's constant is just the dimension of force divided by the dimension of the displacement. So the dimension of force I have shown you just now is just mass times acceleration, right? So it's mlt minus 2. This is the length. So this is mt minus 2. Okay, so in other words, SI unit for the spring constant is, so you can either call it because this unit is Newton per meter, so we can say that this is 1 Newton per meter, or purely in SI units is 1 kg per second square. Okay, so that is the SI units for the spring. So yeah, it's almost 12 already. Wait now, let's see. Yeah, so x, yes, Kaishan, x is the center of mass of the object. Actually it's both, because we assume it's a point, right? So it's one big point. So we assume the object is small enough. Yeah, very sad, right? Oh, yeah, the enemy's name becomes its own. The Newton is still there, so we should call it a Hooke. Yeah, I think I heard this story before. Hooke died in a toilet. Yes, x is a scalar instead of a vector. So my notation here is that so my vector notation, right, is my I show you my vector. So I have a vector r, right, and then in your high school you say like this, right? I say xi plus yj. So this is the magnitude, and then if I put this in, I will get the vector in the x direction, and this will give you the y direction. Yeah, actually the science in the olden days, right, like super a lot of drama. Like all this Newton arguing each other, and then another drama you should look up, right, is the Bernoulli. So the Bernoulli family, right, the Bernoulli is a family of mathematicians, and then even though they're the same family, they always fight against each other. Like it's like a Hong Kong TVB drama, you know, the Johann Bernoulli and Daniel Bernoulli are two brothers, but like the TV drama, like wow, they are competing against each other, fight against each other, all this kind of thing. Anyway, let us take a break for about 5 minutes. I will stop the recording. Yeah, the Bernoulli is the legendary family. Then what else? Anyway, let us take a break for about 5 minutes, or 5 minutes plus, right, around there. Once everybody come back, we will continue. I will start recording now. Okay, everyone's back, right? And everyone can still hear me? Okay, yes, thanks. Okay, so luckily my mic is holding. So let's yeah, so about related to this, right, related to the question, because just now I draw the picture I draw is too big. So it's as if the center of mass of the object is here, and then the point where you attach the spring is here. And actually, the question makes sense, because what Hooke's law is calculating is about the spring itself, right? So because the spring can only know how much it stretches, so it should be the point of attachment. But we are assuming that this object is small enough. We are assuming object is small enough that the size of the object doesn't really matter. So the center of mass and is very close to where it is attached to the spring. Okay, so and then what I want to say is, in these few chapters we assume everything is approximately a point mass. So like, even though I draw like all these big objects, right, m, right, notice that in all our calculation we look at the forces, that's fine, right, but we don't really care what is the size of this object, right? We didn't care. So whether, even though if it's a large object or not, it's still like we treat it like a point mass, basically. So yeah, so related to this question is so if you ask, right, you're asking, well, if the size of the object is not negligible, then what do we do? So that one we will worry about it later. Okay, so right now we treat everything as a point mass, and for cases where we account for the size, shape of the objects, we will cover this in the, I forgot what chapter, in the rotation chapter lah. Rotation. In fact, we start covering this in momentum already. Linear momentum. So in linear momentum is where we first learn how to calculate the center of mass, right? Why did we treat everything as point mass? So actually it will be proven in the momentum part later. So even though the size of the object is a huge box, right? A huge box sitting on a slope and all this kind of thing. But once we calculate the center of mass, then we just treat everything as the motion of the center of mass. Yeah, so right now the size of the object doesn't affect your situation, the forces. Okay. The reason why size will be important, right, is because, like, for rigid body, if I exert a force here, and then if I exert another force here, okay, so most of the time we assume it's all parallel, they cancel each other. But for a rigid body, right, let's say like this pen, okay, if I exert a force here and then exert another force here, it will rotate. So that will cause a rotation to the object, and that is because this pen is not a point particle, right? So if I have something like a single point, okay, something small enough, okay, whatever you do, it will, even if it rotate, it doesn't really affect, right? The position or center of mass is always there. Yeah, does that make sense, what I say just now? So yes, okay, good. Yeah, so if you don't understand, ask me further, because I was like just talking some stuff. I don't know if that makes sense or not for everyone. But so let us continue. Okay, so we have introduced the Hooke's law already. Even though I wrote this in vector form, but we seldom use the vector form, because most of the time we already know the direction, so we just say it's minus kx, right? The minus there is always negative to whatever your x is, because if your x is negative, then you get a positive force. If your x is positive, you get a negative force. So that's the only thing to remember about it. So it's actually very simple, right? Nothing complicated about it. So let's try to work out an example. Okay. Over here. So we are in Hooke's law now. in the first example. So in this example, right, we have considered a block of mass m suspended from a spring of Hooke's constant k, right? The block sits on the slope of angle alpha. If it's in equilibrium, I can calculate the extension of the spring in terms of mkn alpha. So it's basically this picture. Okay, so let's try to solve this. Full screen. Okay, so what we have here is we are doing example 2.2.1. Yeah, by the way, I couldn't find in the Wikipedia how he died. So I don't know how he died in the toilet. The story where I couldn't find it yet. So I have this situation, right? I have a block sitting on the slope and is attached to a spring. Okay, and now we can try to draw the forces acting on the object. So this object is having mass m, therefore I have the mg as usual, right? It is sitting on a surface, so I'm going to have a normal force and because it is hanging from the spring, right, so it will try to, is hanging down, so we can imagine that the spring force, we are stretching the spring now, so the spring force is towards this direction in the kx. Okay, clear? Right, so it's trying to hang down, so it's kx. Now let us try to solve this situation. We try to resolve our forces. So I'm gonna do the same thing. Okay, so I will choose my coordinate system like this. It doesn't matter how you choose, as long as it's correct, it's fine. So let's resolve everything in the y direction. So my mg will resolve this way. I will get mg cos alpha, and then yeah, that's the only thing to resolve. This one is perpendicular, so that's all. So now in the x direction, my mg resolve will be mg sine alpha. So I have two directions now. Let us look at the direction that is perpendicular to surface. Okay, so what are the forces that is perpendicular to the surface? Is here and here, so only these two, right? So only these two, and then there is no acceleration along this direction, so I'm just gonna skip the details. We already know that the normal force should balance out with this force over here, right? Alright, so these two balance, and then how about parallel to the surface? So the forces parallel to the surface is this one, try to pull it up, and this one try to drag it down, right? So we got kx minus mg sine alpha is equals to, well, this system is in equilibrium, so this is 0, right? I'm showing you to do both directions, it's just as a practice, but the question is really looking for only x, which we can already get the answer from here. So my x is just mg sine alpha divided by k. So we just plug in the numbers, and that's how you get the spring extension. Okay, so again, we still can get our normal physical interpretation. Notice that it changes depending on alpha. So if alpha is very small or 0, if it's 0, it's on the flat ground, sine alpha is 0, x is 0. So on the flat ground, you do not need to extend the spring, right, because it's already in equilibrium. But if I raise alpha up a little bit, the gravity will try to pull it down, so it will make the spring stretch a little more until you get 90 degrees. So 90 degrees, all your forces is due to the weight coming down, so it will stretch by mg over k. Sine 90 is 1. Okay, so this is the physical interpretation. And yeah, so it's a good habit to think about the physical interpretation once we got the formula. This is important to relate your mathematical calculation to physical reality, because sometimes it's not always the case, right? Sometimes you can't always get this. Okay, so that is example 2.2.1. And so this is how you solve a spring type of question, right? So right now, let us talk about another kind of force which is a bit harder than spring, which is now we are talking about friction. Okay, so let's talk about friction. Let me double check. Am I still recording? I am. I'm still recording here. So let's talk about friction. Have you guys learned friction in your high school before, or this is the first time? So I think some, depending on what country you're from or some school, they may or may not have learned friction. I'm not sure of the syllabus. It's been so long. So yes, only a bit. Okay. Yeah. So maybe only a bit, and it's partially because the friction is a bit tricky concept. So let me try to define friction carefully. Okay. There are two types of friction that we want to learn here. So let me just write this out. Two types of friction. Okay, which is static and kinetic. Okay, so static and kinetic, and we will learn this one by one. So let us start with static friction first. Okay, what is friction actually? So friction, right? Let's start with what we know in everyday life. In all our Newtonian mechanics so far, if we put something sitting on the ground, we assume it is a smooth surface. But in real life, right, not everything is smooth. Okay, so if you put something on top of a surface, and then if you try to drag it, okay, if you try to drag it, then it will not be smooth. That means there is some force, additional force acting on it. This force is due to friction. Okay, so there's two types of friction that is happening. The static and kinetic. So kinetic is when the object is sliding or scraping against the surface. Okay, so what I mean is relative motion. That is kinetic friction. But the other friction is static. Static friction happens when there's no relative motion. So this one is not moving, right? It's not moving, but as we have learned, right, if I put object on a slope, right, it will accelerate as mg sine alpha if the surface is smooth. But if I do something like in real life, right, if I tilt this by some degree alpha, it still haven't fall down yet. Okay, it still haven't fall down yet. Okay, the force mg sine alpha is not the net force. Okay, it doesn't give acceleration. The reason is because the net force is zero. There is some other force to cancel the mg sine alpha, and that is the friction. Okay, so that is static friction. But of course, right, if I increase the angle by too high, it will eventually start to slide down. Okay, so static friction can only last until a certain point, and then it will start to slide. We can also experience this, like let's say you have a chair, right? So I don't know how to show something. So let's say you have some object, right? You have some object, and then let's say you have some big box sitting on the floor, and then you try to push the thing, right? At first, when you try to push it, you exert your own force. You try to push it, the box cannot move. Too heavy. I mean, we say too heavy, but what we are learning now is because there is a static friction that opposing your force, so that the net force acting on the box is zero, so the box cannot move, right? So you try to move a box. So you try to, if you want to still make it move, you push it harder and harder. That means you give it more and more force. If you push it with hard enough force, suddenly it can move, right? So suddenly it can move. That means at that stage, if it finally move, that means the static friction is no longer able to stop you from moving. It's no longer able to cancel your force. Then the box can move. Okay, so this is the strange behavior of static friction. It can stop you from moving, but if you are strong enough, you can overcome the static friction. Once you overcome the static friction, no more static friction. Then it starts moving. Okay, so that is the idea, right? Is even though when we draw free body diagram, it's very weird, but it comes from our everyday we do this all the time, right? Move box, move the table, move the chair. It's all this is overcoming static friction. So, but in terms of our physical definition, what is a static friction? It is the force that keeps an object fixed to a surface. Okay, so fixed to a surface means there is no relative motion. Okay, between object and surface. So that is static friction, and as always, right, every time I introduce a new force, we need to learn how to figure out its magnitude and direction. So for static friction, right, it's very weird. Magnitude and direction is whatever. Okay, there's no formula yet, but I will teach you how to handle it. But for now, right, just remember that magnitude and direction is whatever, as long as whatever that keeps the object fixed to the surface. That's why it's very weird. It seems like it could be anything, as long as you keep it fixed to the surface. Okay, so that is static friction. Let me explain to you using a simple scenario, right? I was talking about trying to push a box, right? So let's say I have a box on the ground. Okay, so this is now this is not smooth. That means I have friction now. I have a box, okay, on the friction now. So let's say the box is in equilibrium, so definitely it's not moving and not accelerating. Okay, and imagine I'm trying to push a box. So if I push a box, right, I'm exerting a force over here. Okay, so I try to push a box. But it seems like if I exert a box, the box cannot move. Okay, why does the box cannot move? So the box cannot move is because the acceleration is 0. That means something must be causing it to have 0 net force. Okay, I have one force here, but there must be something to make it 0 net force, and that is friction. Okay, so friction. Okay, this one. Okay, so why do I draw this direction is because I want to cancel this force, so it must be opposite. Magnitude and direction is whatever that keeps it fixed to the surface. So keep it fixed to the surface like this. Okay, so let's say I write in vector notation. Okay, so let's say I don't know the direction, right? You do not need to assume, because in most cases we shouldn't assume. So let's say I have this one, and then I plus some other force, and then this is my net force, and by Newton's third law, it is equals to mass times acceleration of the system, but my system is having 0 acceleration, therefore my F0 plus the friction force is equals to 0. Or then in other words, I have found that my Fs is equals to negative F0. Okay, and my F0, right, is some magnitude in the I direction positive. So if I plug in this expression, my friction force, I can now determine my magnitude now. It is the magnitude of F is just F0, and then F0 in the I direction. So if this F is in the positive X direction, then my friction is in the negative direction. Okay, so I know this is very simple, but let me check whether everyone is following so far. Your high school teacher said that cause of friction hasn't been found out clearly. Yeah, that's why. So that's why we can only make these general arguments like this. And unless you're referring to what is actually friction, right? So friction is the interaction between the two surfaces, and then you need to consider, okay, you need to look at interaction between two surfaces is actually the atoms and molecules of the two materials. And then these two materials, atoms and molecules, they have this van der Waals or electromagnetic interaction that is very complicated, but at the end you can just for our situation just study in this sense. Okay, so hopefully it's simple, but it's going to get very complicated soon. Okay, so let us if everyone is okay with this, then it's fine, right? So this is where the magnitude and direction is whatever keeps the object fixed to the surface. If I push it to the right, my friction force is left. If I push it the other direction, the friction force is the other direction. Okay, and then right, notice that this friction is the magnitude is exactly the same as F0. If I push at 1 Newton, the friction is automatically 1 Newton. If I increase to 2 Newton, the friction also automatically 2 Newton until it reaches a maximum. Okay, so what I have here is that and this is another property of static friction. So static friction can only go up to a maximum value, maximum magnitude. So that means the static friction, right, is it can automatically match with your force, but if you go higher than its maximum, then you cannot. Okay, so in other words, what I'm trying to say is the magnitude of static friction can only exist in this domain between 0, right, until some maximum value. If you learn this in high school, you have seen this formula, mu s times the normal force. So we can calculate this based on the normal force, right? So for this problem, you need to determine the normal force as well. So we look at the vertical forces. We got mg here and then n here. So for this question, n is equal to mg. So it depends on the normal force through this way. Okay, so that means if I exert a force where F0 is greater than this thing, then the object will move. Sorry, object will move. And I forgot to say, what is this? This is mu s. So this mu s is the coefficient of static friction. Okay, everyone follow so far? Yeah, between the electron cloud. I'm not very familiar because this is under solid state physics, right? Yeah, so you have the object, like it consists of atoms, right? It depends on whether it's metal or polymer or things. You have the electron, you will have the electron cloud, but I don't the electron cloud on the interface will interact with the electron clouds and the ions on the other side, and so it's a very complicated behavior, but I think in some cases you can solve it exactly for certain materials in solid state physics, but I'm not sure how to do that. So you need to know quantum mechanics to solve this situation. Okay, now this is where it starts to get complicated. Okay, and this is the case where the complicated case is where the acceleration of the system is not 0. So let's look at a moving object. So let's say this is some trolley or some car. This one is a rough surface. If it's a rough surface, and then I have an object sitting on top of the rough surface, and then there is a force exerting on this rough surface. So this force could be the wind, right, blowing on this thing. Okay, so and this whole system is accelerating at a that is non-zero. Okay, so I can write this in vector form. So a is some magnitude in the x direction. So let's say the system is moving this way, and then I have some force that is in the I direction. Okay, now this thing is moving. This thing is moving, but it's still considered static friction between the box and the car, right? Because they are moving together. The key point here is that there is no relative motion. This system is moving relative to the ground. So M is moving relative to the ground, that's fine. But M has zero relative motion with this trolley. Okay, so no relative motion. Okay, so no relative motion means that even if there's a force, the box will stick to the car and they will move together. So moving together means no relative motion. Okay, so if no relative motion, then what is the net force acting on this? So there is some friction force acting on this surface here. It could be forward, it could be backwards, right? So let me make this clear. I don't know yet. Okay, so don't know yet. Okay, whether it's this way or this way. Okay, the whatever it is whatever that keeps the object fixed to the surface. Okay, so that's why we don't know yet. As long as we make the thing stick to the surface. So let's look at the net force acting on this system. So the net force is this force and then plus this unknown force. So I got this force I plus this unknown force friction. Okay, and this system is accelerating at A together. So this is mass times acceleration. So this is the acceleration relative to the ground. Okay, so accelerating relative to ground. Okay, and this is at this stage this is unknown. Okay, but even though if this is unknown, we have this equation, so we can solve it. So we just got this. Bring this over, so I got MA minus F naught I. In fact, A is in the I direction, right? So I got MAI unit vector and then FI unit vector. So I got MA minus F0. Everything is in the I direction. Okay, so I have my formula for the static friction in this case. So notice that this number could be positive or negative. Okay, so notice that, okay, so if there are two cases here, right? So if MA is so if MA minus F is a positive number, in other words, which is to say that if A is greater than this number, then, so this is case 1, then my friction, if this is positive, right, then my friction is actually pointing in this direction. Okay, but on the other hand, if my acceleration is small, okay, if my acceleration is small, then, or in other words, if A is smaller than this, then my static friction is pointing to the left. Okay, so it depends. So now it depends on acceleration. So if the acceleration is small, the friction is still to the left to keep it fixed to the surface. But if this is accelerating at a very fast number, then you actually need the forward direction to keep it fixed to the surface. Okay, in fact, if F is if there's no external force, right? If there's no external force and there's some friction, when the trolley accelerates, then the friction will make sure the box accelerates together. Okay. On the other hand, right? If the other case is if MA minus F, the magnitude is greater than the coefficient static friction times normal force, then no more static friction. So the box M slides over the surface. Okay, so this F could be 0 as well. Okay, so if F is 0, that means no external force, then you accelerate. This is again everyday experience that we can imagine, right? Let's say this is a lorry, right? So if you're a lorry, you put a box on the lorry. Okay, and then if you want to move a box carefully on the lorry, you must not drive too fast, right? You must drive slow enough so that the box is sitting properly on your lorry. But if you suddenly brake, right? If you suddenly brake or you suddenly accelerate, you have an acceleration that's suddenly a very large number. Then you overcome the static friction. Then the box will just slide in your lorry, right? If you suddenly brake your lorry, then the box behind your lorry will slide on your lorry. Yeah. So, do you understand what I'm talking about? I hope I make sense, right? The calculation is like, in the context of what we normally learn, it seems a bit unusual, but it's what we experience in the everyday life. Okay. In fact, I can even do this, right? So I can show you this way. Okay. So now this paper is is this thing here. Okay. Then this is my box of mass m. So if I accelerate, as long as I accelerate at a number that is smaller than this, then I maintain static friction. So if I accelerate very, very slowly, static friction will make sure this box moves together with this paper, right? This mouse. There is no direct force acting on it. So why is this mouse moving? The mouse is moving is because the static friction between the paper will make the mouse move, right? Then I'm not exerting any force on the mouse. Okay, but if I suddenly accelerate very fast, okay, if I suddenly accelerate very fast, it will slide off, right? I think it's not in the camera. So if I suddenly accelerate my mouse too fast, right, then static friction will break, and there's no more static friction. It will do this. Okay, so that is when static friction is exceeded, it will slide over the surface. Okay, any question? Don't understand this number, greater than 0. Oh, actually, maybe there's nothing much. It's just to say whether this force is positive or negative. That's all. Right? If this is a positive number, then F is pointing to the right. Right? If this is a negative number, then this is a negative direction. That's all. I mean, nothing too complicated about it. Okay. 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 So, no question. Yeah. So this is a more general situation. The example will be a more direct case. So maybe it will be easier to understand with the example. So the lorry situation is in this example. I have a box of mass m sits on top of the lorry. Coefficient of static friction is this number. What is the maximum of the acceleration of the lorry so that the box does not slip over the surface? So this is example 2.2.3. 2.2.2. Okay. 2.2.2. Let's draw the lorry again. Am I still recording? I'm still recording. Still recording. Yes. So I have a box M. Over here is a rough surface. Right. So let's try to draw the forces acting on this box. So as always, there's a mg as normal, and I'm going to need the normal force later. Okay. And then what else? So this whole system is accelerating at A. Then obviously the box will accelerate together at A. So what is the force that causes it to accelerate, since there's nothing else touching it, right? So the only force that will cause it to accelerate, this is the static friction. So that's why we got this, right? So that means the net force acting on the box M is, there's only static friction, and by Newton's second law, it is mass times acceleration. Okay, so as I was discussing just now, right, static friction could be any number between 0 and the maximum. Okay, it depends on your acceleration. If I accelerate and get this number, your static friction will automatically put its own correct number here until its maximum. So how do I find the maximum? So if A increases, the static friction will increase. So I can increase until the maximum value. When A is having some maximum value, the static friction will reach its maximum value here. Okay, so then this equation becomes okay. So one thing I want to emphasize is that the difference between this line and this line. This equation means that for any A, the static friction can be anything. I just want to find the maximum point where the static friction cannot resist anymore, right? So it cannot sustain static friction anymore. So I got this maximum. Okay. So so this is equation 1. But then if I calculate the vertical forces, right, there is no vertical acceleration, therefore the n is equals to mg, and that is where I use this to substitute into here. So mu s mg is equals to m a maximum, and then notice that the mass actually cancels each other, so a maximum is equals to mu s g. Okay, so notice that if you want to drive boxes carefully in your lorry, right, your maximum acceleration is actually independent of the mass. So it depends on your coefficient, right? Maybe the coefficient depends on the type of mass and the material of the box, but as long as it's there, it's independent of mass. So whether the box is heavy or not, the A maximum is given by this formula. Okay, so maybe this example is easier, makes it easier to understand the static friction. Okay, yeah, let me know if you have any other question. Otherwise, the next example shall be attaching this to a spring now. So now this is where questions can become complicated. So now we can mix and match different situations. Okay, so in this example, we look at a box of mass m. Okay, it's sitting on a rough surface with this coefficient of static friction, and then spring constant is 30 Newton meters. Sorry, I think it's per meter, right? Typo. And extended by x. So what is the maximum extension so that the box doesn't slip over the surface? Okay. The max where f is mu n. Oh, okay. So what we have here, right, is this situation. So right now, right, I think it will help if I put some concrete numbers. So let's say let's consider an example, right? An example, let's say my mu s is, for this, we are still doing this, right, to answer your question. Let's say mu s is 0.4, and let's say this box is 1 kg. Okay, so then from here okay, so let's calculate my maximum acceleration. So from here my maximum acceleration is going to be 0.4 times g, so it's going to be 0.4 times 9.8, right? So we got 3.92. Okay, so that means, right, as long as my acceleration is less than 3.92, at least the magnitude, okay, the box will be static friction, so box will be fixed on the surface. Okay, so that means let me, for example, right, so that means if I accelerate, let's say 2 meters per second square. Now 2 is smaller than this, right? So if 2 is smaller than this, that means the static, still within static friction. So that means the equation is still valid. Okay, so still within this equation is still valid. And then in this, if I accelerate at this number, I can actually calculate my static friction force. So this is 1 kg, right? So 1 kg means my static friction is just 1 times 2. So my static friction is just 2 newtons. So in this case, my static friction is 2 newton. Okay. Now, if I accelerate at some other number, so let's say 1 meters per second, okay, it's still within static friction, right? It's still smaller than 3.92, so still valid. My equation is still valid. F is equals, the static friction is equals to mass times acceleration. So over here is 1 newton. Okay, so notice that the static friction automatically changes if you change your acceleration. It is because of this equation. As long as my whatever acceleration I'm using is less than 3.92. Okay, so if I accelerate at 5 meters per second, okay, so if I accelerate at 5 meters per second, it is more than maximum already, right? It is more than my mu sg. So if it's more already, then no more static friction. That means if I accelerate too fast, the box will slide over the surface. Okay. Yeah, 3.92. Oh, the power. Did I put it wrong? 3.92. Yes. Correct. Then the rest, I put it correctly. Still wrong here. This is correct. Yeah. Okay. Does that make sense to you? Okay. So that is the funny thing about static friction, right? Sometimes it's this number, sometimes it's this number. It depends automatically on what you do to the system. Okay, so what you do to the system, the static friction automatically changes to agree with the Newton's law. Until what you do is too much, accelerate too fast or too strong, then you cannot already. Then it will start to slide over the surface. Okay. Okay, so actually we have one more example, but there's not enough time. So yeah, I guess either we will skip it or we'll do it in the next class lah. Okay, so it's already almost 12. Does anyone else have any more question to address? Since I have no more time, there's not enough time to start a new example. Oh, which direction of friction? Yeah. So in the example, right, I accelerate in the positive x direction. So I choose a positive number. This is positive 2. Right? Positive number, positive 2. My x positive is in this direction. So if I choose a positive x direction, I plug in, I will get a positive friction number. So my friction force is 2 newtons to the right. So same thing here. If I use a positive number, I will get positive. But if I drive in the other direction, so if I drive in the other direction, negative. If I plug in a negative number, I will get negative 1 newton. Then my friction force will now be 1 newton. Last part of the note, which you mean this? Or this page? Yeah, so you tell me, this is page 7, this is page 8. By the way, I will scan and upload after this class. Okay, so I think you mean this, right? You want to see this? Is that what you mean? Let me check. May I assume the friction is relative motion only? Yes. So yeah, so the friction is the relative motion between these two, right? and then that's not relative to the ground, so it's relative between these two. By relative motion. Okay, so yeah, anyone else have I answered all your questions? I forgot. You can see this note, right? Okay, clear? Yeah, so friction is the probably the trickiest one, the trickiest concept in this chapter. Next part, there's actually drag force. Is the equations are more complicated, but I think it's easier to understand. This one is conceptually is a bit harder to understand. So yeah, so you can read through the notes again to see anything else I did not say. I probably covered everything already. So you read through the notes and try to think about these examples. So if you still have any more questions, you can ask me in the next, ask me here or ask me in the next class. But other than that, that should be all the time we cover for today, I think. Right? So we have talked about friction, then we have only two more things in chapter 2. So the resistive force, drag force, and then about the centripetal force. But those are relatively easy compared to friction, I feel. Okay? So okay, so if there's no other question, then I think that's all for today. Let me stop the recording. Where is it?